This slide set is going to talk about the behavior of gases. So you need to pick up your graphic organizer for 3.3a, and it looks like this. And what you're going to do, you're going to fold it in half. And so you have the front of your graphic organizer. And then you're going to cut on the dotted lines just right here. Only halfway and not all the way through. So only from here to there. That's the only place you're going to cut this graphic organizer. So this line, and this line, only to the middle. So this is what it should look like. You should have these flaps when you cut only to the middle of the page. And this is going to serve as a graphic organizer for our slides for gases. You can save this part of cutting until the very end if you want to, if you think that'll help you take notes. So on the inside, you have notes that you're going to fill in as we go along. So there's 4 properties of gases that we need to talk about. We have expansion and compression, low density, fluidity, and diffusion and effusion. So to start out with, when a gas is heated up, the particles move faster. And remember that gases have pressure when they're in a container. And so in this example, you have the balloons. And so you can see that the gas is expanding within the balloons. The temperature is increased by putting the balloons on the table at room temperature. The balloons were put into liquid nitrogen, which is super duper cold, which slows down the gas molecules in the balloons, and we get a decrease in volume. So here you see the expansion of those gas molecules within the balloons. Gases can also be compressed, and when we compress a gas, we put it under more pressure. Density. We've already gone over the phases of matter, solid, liquid, and gas. We also have plasma. We know that gases are bouncing around like crazy, going speedy fast, and they're the least dense of the phases of matter that we're going to talk about. Diffusion is another property. Diffusion is the movement of particles from a higher concentration to a lower concentration. So if I happen to open a bottle of vanilla in the back of the classroom at the beginning of class, I wouldn't be able to smell it at my desk in the front. But the person sitting right next to that bottle of vanilla, not knowing it was there, would start sensing the smell of vanilla. Eventually, the smell of vanilla would fill the entire classroom because the gas of that smell is going to keep bouncing around the classroom. And it's going to go from the high concentration within the vanilla bottle to the lower concentration, which would be the air in our classroom. In the example on the slide, you have bromine gas on the bottom flat cylinder, and you can see that that gas is diffusing up into the cylinder they put on the top. We have to put that cylinder on the top so that we can see that gas diffusing, or else the bromine gas would just randomly diffuse into the environment and we wouldn't be able to see its diffusion taking place. So this is bromine gas diffusing from the bottom cylinder into the cylinder that they place on the top. Effusion is kind of like diffusion, except that gas particles can pass through tiny openings. This is important on the cellular level within our bodies. Fluidity. Gas can be classified as a liquid because it has the property of being able to flow. We can see in the bottom left picture that the smoke, aka for us, the gas, flows like a liquid out of the container. We can also see the wind tunnel on the bottom right, where smoke is used to show how the air flows over the car. This is an example of seeing the aerodynamics of a car. There are three factors that we need to pay attention to when we're talking about gases, and that's volume, temperature, and pressure. If you remember from our previous discussions that volume is the amount of space that something takes up, and the SI unit for volume is the liter. And so the green gas particles, we wouldn't have a concept of the volume of that gas unless we put it into a container. And so in the balloon, you have the pink gas molecules, and depending on the temperature of those molecules will depend on how much of the volume of the balloon is inflated. We also have to take in not only volume, we also have to take in temperature and pressure. We could measure the yellow, gas molecules, but we'd have to define what the container is for us to take that measurement. Temperature is a measure of how fast particles are moving. The SI unit that we'll use is degrees Celsius. So in temperature, we're talking again about particles moving. So on the right, the blue molecules are moving slower than the red molecules on the right. And you can see by the thermometer on each side, the temperature. So this should make sense to you, that the higher the temperature, the faster the particles are going to move. You also should note that this is a solid in this example and not a gas because the particles are being held in place. This is just to illustrate that particles move faster when the temperature is higher. When we look at gases, the example on the left is an example of a lower temperature, and the example on the right is an example of a higher temperature. So gas molecules are going to move around faster when there's more heat energy. Then we have to talk about pressure, and pressure is the force per unit area on a substance. The SI unit is pascals. So if I just lay my hand on my desk, it's going to have the force of gravity. If I push on the desk, then it's going to have the force of my hand on the desk and the added energy of me pushing on the desk. So how much of my hand touches and how much I'm pushing down is going to affect the pressure on the desk. We will be doing more with pressure and formulas later on, but there is your triangle for the formula for pressure. It is pressure equals force divided by area. There are several laws that we know about gases. A law is something that has withstood the test of time and has had many experiments done on it to try to prove it false. Remember, science has to be falsifiable. So there are some things that we agree upon about the behavior of gases. And all of this leads to the ideal gas law, which you'll use later on when you get into high school. The first of the laws is Boyle's law. And Boyle's law states that there's a relationship between pressure and volume if you keep the temperature the same. So remember, we have three variables: pressure, volume, and temperature. In Boyle's law, temperature is kept the same. It's important to note on each of these laws which variable stays constant. So if we have gas in a container, the gas will expand to fill the entire container. So if we had a box, and in the box we put in some helium. At the very first part, the helium is where we put it in the box. But the gas is going to expand to fill the volume of the entire box. It won't just be in the corner, it'll fill the entire space within. The pressure that we measure in the box is going to be the number of collisions of the gas molecules on the wall of the box. So if we increase the temperature, is going to stay the same, sorry. So we're going to show some examples of Boyle's law. So temperature is going to stay the same. If we decrease the pressure, what's going to happen to the volume? And if we increase the volume, what's going to happen to the pressure? This slide is to let you know that these are PEEPs, and they're going to be in one of the examples coming up. So there's a direct relationship in Boyle's law. If you increase the volume, you decrease the pressure. So in the example, you have the PEEP, and the PEEP is in a vacuum. The PEEP has air trapped inside of the gelatin and sugary mix that it is. And the pressure outside is less than the pressure inside the vacuum. So the PEEP is going to expand to equalize the pressure. Temperature isn't going to change, but it's going to expand, which means the volume is going to increase. If we release the vacuum, meaning that we're not controlling the pressure within the glass container anymore, the pressure increases, which causes the PEEP to shrink. It causes the air within the PEEP to compress instead of expand. So decrease the volume, increase the pressure. Increase the volume, decrease the pressure. Another example. At the end of the animation, the gas particles have less space to bounce around in. This will increase the number of collisions that happens to the wall of the container. This increases the pressure. Pressure is how many gas molecules are hitting the sides of the container. If the pressure was too great on the sides of the container could burst. You can see the pressure gauge up at the top of the container. As we decrease the volume, you can see that the pressure is increasing. Another example is putting marshmallows into a vacuum. Same scenario as the PEEP. Oh, marshmallows is spelled wrong. Must fix that. And in the bottom right is shaving cream. So same thing, both substances have air within them. So if we make the box bigger, That gives the gas more space to expand. Gases are going to do that. No matter what kind of container it is, the gas will expand to fill the entire container. When this happens, that decreases how many collisions the gas molecules are going to have with the walls of the container, hence lowering the pressure. The opposite happens in that if we decrease the volume of our box, that is going to give the gas molecules just less space to bounce around in, so that would increase more collisions with the side of the box, hence increasing pressure. So the relationships you need to keep straight, and you also need to remember what's held constant for each of the laws we talk about. So this is a graph of Boyle's law. With the temperature being kept constant. This is an example of a graph being plotted to show the relationship between pressure and volume. You can see as we decrease the volume, or the value on the x-axis, that we increase the pressure, the value on the y-axis. And we represent this data with a model, which is the curve that we put on the graph. Next is Charles's law. Charles's law shows that there's a relationship between volume and temperature if we keep the pressure constant. So again, in each of these laws, remember the variables and what's held constant. If we have an expandable container, meaning that if we want to keep the pressure the same, the container has to be able to move or expand and contract based on the pressure that we have. So in the two examples, you can see that the pressure are the same on the slide, but the volumes are different and the temperatures are different, but the pressure is the same. So in this example, they have water in a flask and they heat the water to boiling, which causes water to change from a solid to a liquid. The water molecules gain enough heat energy to escape the liquid phase and turn into a gas. And those gas particles expand and fill up the balloon on the top of the flask. If we didn't have the balloon on top of the flask, we wouldn't be able to see the gases being released because the gases would randomly fill the environment of the classroom. So we increase the temperature, the molecules move faster, which increases the volume. In this example, they have a helium balloon, and they take the helium balloon and they place it into liquid nitrogen. Liquid nitrogen is super duper cold. And so when the balloon is put into the liquid nitrogen, the particles of gas compress, they move slower. So if we decrease the temperature, we decrease the volume. The balloon gets smaller. When the balloon is put on the table, the molecules of helium within the balloon heat up, expand, and inflate the balloon. This is the same example with the hot water, the boiling water blowing up the balloon. The same thing happens if we take that closed system, meaning the gas doesn't escape and it's not added. If we put that flask into cold water, or in this case, I think they probably have a batch of ice water, the temperature of the gas molecules decrease, which hence lowers the volume of the balloon. Another example Liquid nitrogen is quite dangerous, so it's not something to mess around with or play around with because 320 degrees is pretty darn cold. And here's the graph of Charles's law, that if you increase the volume, you're going to increase temperature. If you decrease the temperature, you're going to decrease the volume. Guy-Lussac's law? His is a relationship between temperature and pressure. When we keep the volume constant, again, volume, the amount of space something takes up, temperature, how fast the particles are moving, and pressure in the terms of gases is how many collisions the gas has in the container. As we add heat energy to a gas, the gas molecules move faster, they speed up and expand. If we have a rigid container, which in this law it has to be because volume stays the same, the particles cannot expand. So if we had a container that the sides wouldn't expand or there wasn't a topper on it that would move up or down, that is going to create a problem if there's not enough pressure inside the container or there's too much pressure inside the container. A pressure cooker works in that it creates a higher pressure than just boiling water. The problem is that if you have something that you're increasing the pressure in and you don't watch it, you could be causing an explosion. The pressure cooker would eventually burst because the metal sides wouldn't be able to withstand the pressure of the gases inside. So that's why there's a little topper on top of the pressure cooker to allow some of the water vapor to escape, lowering the pressure to where it's not in a dangerous zone. Increase the pressure, increase the temperature. Some recipes call for things to be cooked in a pressure cooker, meaning that we can increase the temperature inside the pot by increasing the pressure. Another example, we have a metal container that's closed that they heated, and then they rapidly cooled off the container. The pressure outside of the container is much higher than the pressure inside the container when the gas molecules cool and compress. And then we have Guy-Lussac's law graph. So in science, these all boil down to what's called the ideal gas law, which is PV equals nRT, pressure, volume, constant, temperature. So it takes into account all the laws that we've talked about today.